chemical stoichiometry. Definition simply is this is the mathematics of chemistry. Now, the math that you need for this course is exclusively algebra. And working with basic ratios and proportions, linear equations, and so forth. In second semester, we use a very classic derivation of what we call the integrated rate law, which applies some integral calculus, but it is very classic in the context of it. Having said that, that's for this course, but as you move forward in higher courses, especially in physical chemistry areas, as much math as you can squeeze into the brain cells will do you well in this. When we talk about the math of chemistry, it really revolves around what can you do with a chemical equation. Okay? What's the math of the chemical equation? The question is, what can be calculated from a chemical equation? What is the mathematical relationship in a chemical equation, and how do we apply that in the mathematical solutions? Now, one unwritten issue in the working of math problems in chemistry is being able to visualize the chemistry that's going on, and sometimes that is difficult. The majority of it is in terms of, well, how does the equation change mathematically from the reactant side to the product side, and visualizing a more practical setup and mixing reactants and so forth relative to the numbers. So you're translating a practical environment picture to some mathematical structure. Example would be titrations. This is just an example. Titration is a process by which we separate reactants. Say we have one reactant in a tube called a titration burette. And then maybe a flask and here that we will be have a second reactant. Okay, so that's some, and you've probably seen this in graphics before. But what the idea is, reactant 1 plus reactant 2 will go to products. And there is a mathematical relationship between these, and nature is a proportional relationship. Between the reactant 1 and reactant 2. Well, all of them, whether it has just 2 reactants or one on one side and several on the other, there is a relationship, not only to the reactant side, but also there is a proportional relationship to the product side. Now, the issue is, what do I mean by proportional relationship? It means that if we take an equation, consider this equation. And most of you can read this without any trouble. Based on the synthesis of ammonia. Well, when you look at this, the coefficients of the relationship can be interpreted in several ways. One of the ways is called moles. When you look at this equation, moles of the reagent that you're looking at will be the coefficients. And of course, it's understood to be 1 right there. So we say 1 mole, 3 moles, and 2 moles. The mole is the quintessential king of chemistry. And I have one rule that I tell students, and you're working math problems like this, that deal with moles in a chemical equation. Take the data, convert it to moles, apply the moles to the equation, solve it in ratio and proportion. That's the simplest way. And then convert the answer, as it will be in moles, back to whatever the problem is asking for. That's the simplest way to go through these things. You can use dimensional analysis, you can use cross-referencing, you can use inspections, but that is the simplest way. Convert to moles, solve the problem in ratio and proportion, and convert to the question at hand. Okay? So what do I mean by the proportionality? Now this is the standard equation. Remember what I said? Standard equation is, it is the reaction expressed in the smallest whole number ratio coefficient. Everybody catch that? Smallest whole number ratio of coefficients. So we can't reduce it anymore. However, that doesn't mean I can't scale it up or scale it down. And you can do this with moles. You can't do it with any other unit or dimension, like grams. You can't just double grams. It doesn't work because the formula weights don't cooperate. Or gas volumes, or energy numbers. It just doesn't fit. But moles fits on every level. Solve all the problems in moles. What I'm saying is you can multiply the entire expression by 2. And I can have this expression. And that will work fine. If I mix 2 moles of nitrogen gas with 6 moles of nitrogen, hydrogen gas, I'm getting there. Now, 6 moles of hydrogen gas, it will always give you 4 moles of ammonia. And that's a balanced equation. You know how to balance equations by inspection and some of the oxidation reduction process. But whether it's oxidation reduction, metathesis, regardless, those mole numbers are always proportional. If I want to cut everything in half, what would happen? Well, that would be 1/2 N2 gas. See if I can get it right. 6 halves, 3 halves, 3 halves H2 gas. And I put the 2 over 2 just for emphasis. Now, there's nothing wrong with any of those. Any of those combinations of reactants will always give you the product side. Another way to say this is, if say you take the first one, production of 2 moles of ammonia always requires 1 mole of nitrogen and 3 moles of hydrogen. So once you're working with the standard equation and you've got it balanced, those coefficients say a lot about everything that you need to know about that equation. Now we're going to work with those more than anything today. We're going to use the rule convert to moles and solve for whatever they're looking for. So, what do we need to know in order to deal with this on a big picture scale? I like this equation because it's got different coefficients on every reagent. Okay, what can we calculate? I'm going to move that over some. Forgive me. I need to get a little more room here. N2 gas plus H2 gas goes to 2NH3 gas. Okay, so the items, what can we calculate? From the chemical equation. So you can set it up like this. Well, the first thing I mentioned is moles. And from moles, we can get mass. And this is called an equation mass, as opposed to formula weight mass, like nomenclature terminology. Particle numbers. And this is proportional to Avogadro's number. That's 6.02 times 10 to the 23rd, and it's given a capital M with a subscript 0 on it. See that? Like that. Gas volumes. And this refers to molar volumes. And typically it's given a symbology V lowercase, subscript M. And finally, energy values. We call this reaction enthalpy, heat of reaction. But to condense everything into something this basic, we should help you understand the bigger picture. Every one of the items below the mole issue are calculated relative to the mole. When we look at this equation, how many moles do we have in each one? Well, it's always the coefficients that in the equation. Now, if you're working with the basic standard equation that's been reduced to the smallest whole number ratio, then of course that would be your standard. And so this would be 1 mole of nitrogen, 3 moles of hydrogen gas, and 2 moles of ammonia. Now, I'm going to define moles in great detail in a minute, not to worry. Very simple. So the first thing is just look at the balanced equation, the coefficients, and you know the moles. Now, mass, what gram weights do each one of these? Well, this says the number of moles times formula weight. That gives you the equation mass on each one of those reagents. So this would be 1 times 1 formula weight. And hydrogen, formula weights of nitrogen. Okay, and that would be 1 times 28 grams, and that'd be 28 grams. It's going to get crowded. Sorry. That's the equation mass that's used in that reaction. Here we have 3 formula weights of molecular hydrogen. Well, that's equal to 3 times 2 grams, or 6 grams. That's the equation weight. for hydrogen. If you had 7 grams, there'd be a 1 left over. There'd be an excess. It wouldn't react. That's what it's telling me. 2 formula weights of ammonia. And that would equal 2 times 17. 4 grams. So 28 grams requires of nitrogen, requires 6 grams of molecular hydrogen to produce 34 grams of nitrogen. Well, that's true. Some people may be able to deal with it, but it's a lot easier up here. You'll see. Particle numbers. Now this is a double-edged sword. You can talk about individual particles, or you can talk about in the real world numbers of particles. 1 mole of any substance contains 1 Avogadro's number of particles. That's the definition of a mole. And I'm going to translate that into something else also. So we have here, if that's the coefficient 1, see I have 1, 3, 2. Those are the moles. Now, I have 1 Avogadro's number of particles here. So that's 1 times 602 times 10 to the 23rd nitrogens. Here I have 3 Avogadro's numbers of H2 molecules. Avogadro's number is still 602 times 10 to the 23rd. Many of you have heard of it. And ammonia. Here we have 2 Avogadro's number of molecules of ammonia molecules. 6.02 times 10 to the 23rd times 2. And that gives you the real number. Okay, yeah, that's the realistic footnote in that consideration. But you can also go in here and say, well, 1 molecule of nitrogen gas plus 3 molecules of hydrogen gas will react to produce 2 molecules of ammonia gas. So you can kind of narrow it down to individual considerations, but in reality, it's always related to Avogadro's number in that row. One of the things I want to make point of here, while this is 2 moles of 2 Avogadro's numbers of ammonia, notice that how many Avogadro's numbers of hydrogen atoms are in there? Be 6. So pay a close attention to that, because I have a couple questions on the exam that'll reach over and grab something like that. How many atoms of hydrogen are involved in this reaction? Just as off the cuff question. Okay, so it's 3 Avogadro's number of H2s, but you got 2 H's in each one, so you double it again. Okay, so 3 times 2, that's 6 hydrogen. 6 times Avogadro's number of hydrogen. So put an X by that. It's kind of a little sub-type calculation, but it is important because you'll have a couple of questions on the exam that'll ask you. And it's just an absolute number of element times Avogadro's number. It's not a hard question. Next is gas volumes. For reactions that involve gases. Now, this little row does not involve solids or liquids. It's only gases. Okay. Well, everybody's gassing this, and that's why I use it and get the most out of this. Well, what is a molar volume? A molar volume, now listen to me carefully. You'll hear this many times again. 1 molar volume is the volume occupied by 1 mole of any gas. Now, underline N. If I have 1 mole of hydrogen gas, it's going to occupy the same volume as 1 mole of ammonia gas, which will occupy the same volume as 1 mole of nitrogen. Doesn't matter what it is, 1 mole, any gas, occupies 1 molar volume. What's the number on a molar volume? And do not say 22.4. Because that only shows up if you specify temperature and pressure. So check mark that. Molar volumes is the whole range of temperature pressure. So in order to get a number to go with this Vm, you have to define temperature, because if you increase temperature, your gas will expand. Think of a balloon being heated. It'll get right there. Or pressure drops, volume increases. So you can't say that 1 molar volume is always 22.4. The only conditions where that molar volume, 1 mole is 22.4 is at 0 degrees in 1 atmosphere. That's standard gas law. And you'll study that in the next chapter in great detail. But right now, this molar volume is related to your equation in the following way. Here's 1 molar volume because the coefficient's 1. So you have 1 molar volume of nitrogen. But you have 3 molar volumes of hydrogen gas, and you have 2 molar volumes of ammonia. Now, what those volumes are depends on temperature and pressure. Only at 0 degrees in 1 atmosphere can you say it's 22.4. Now, having said that, what are the conditions of your standard equation? Remember? Yeah. The standard equation is defined as 0 degrees in 1 atmosphere. Knowing that, now you can put a number in there. Okay? So if all the equations under standard conditions, of course they got gas in them somewhere, is assumed, that's what assumed thing, to be 0 degrees in 1 atmosphere, then you can say that is 22.4 liters of nitrogen. Yeah? Now if it's not 0 degrees, you can't do that. Everybody good on that? It's very important. Now there's a lot that goes with that, but if you'll just boil it down to, well, volume occupied by 1 mole of gas is a Vm. At 0 degrees, it's 22.4 and 1 atmosphere. And that's it for right now. Anything else goes with it will come up in the next chapter. Here we have 3 22.4 liters at 0 Celsius, 1 atmosphere. I can put that in here. And here is 2 times 22.4 liters at 0 degrees and 1 atmosphere. I just don't have enough room to write that. But any other temperature pressure combination, all you can say is 1 molar volume, 2 molar volume, 3 molar volume, whatever. It's given by the coefficient. Finally, energy values. Well, this reaction starts out and undergoes an energy change. We have reactants going to products, and you have what we call an initial energy and an energy final. And the change in energy is the heat of reaction, or enthalpy of reaction. Now, it's, say, delta E is 10 kilojoules. Now, the point here is well, as a matter of fact, this reaction, let me give you exactly what it is. I know what that one is. The energy of this reaction is 91.8 kilojoules. I do know that. Okay. Where it comes from, you'll learn in chapter 6. The thing I'm trying to teach you here is that 91.8 is proportional to the coefficients in here, the molar coefficient, mole coefficient. 1 mole of nitrogen in an excess, say you got more than you need, hydrogen, will give you 91.8. If you double that, you go to 2 nitrogens in an excess of nitrogen, i.e. more than you need, you'll double that energy number. See, that's a standard energy number. That energy number is attached to the standard equation. That's that standard equation energy number. So if you want to scale it up or scale it down by fractionals or multiples, use this moles to scale it up. And if you've heard of limiting reagents before, then it scales up relative to the limiting reagent, because limiting reagent is the substance that when it runs out, the reactor stops. We'll talk about that in detail. Okay, that's what you can calculate. What do we need to know to deal with it? Number one, moles. What's a mole? Okay. 1 mole of substance is the mass in grams containing 1 Avogadro's number of particles. This turns out to be 1 mole of substance is equal to 1 formula weight of substance. So 1 mole of H2O has a weight of 18 grams. It's called, sometimes they call it gram formula weight. Big deal. 1 mole ammonium, 17 grams, gram formula weight. 1 mole H2SO4 is 98 grams. You can add it up. Just the formula weight. It's the mass that contains 1 Avogadro's number. Now, what do you need with this? You need to be able to convert given data to moles. So that you can apply ratio and portion to chemical equation. You can't do it with equation mass. You can't do it with molar volumes in the context I was giving you. You can't do it with the particle numbers. You can't do it with energy numbers. The only one you can do it with, and the simplest way to do it, is from moles. Moles proportional to moles, increase to moles, X. Cross multiply and solve. Given mass in grams. Moles is mass in grams given divided by a formula weight. Now, if you're given moles, whatever they are, then you want to go back to grams. Then it's moles times formula weight. So you need to know these reflexively. Like if I ask you what your name is, you don't have to think about it. You give it to me. Divide by formula weight. Grams. Given. Brain says divide by formula weight. Moles given, multiply by formula weight. You're either going to be going to grams from moles or moles to grams. One way to look at this issue of formula weights in math is like this. One way to think about it. Listen. How many formula weights are there in a given mass? That tells you, basically, it's a ratio thing. So if I got a certain number for my formula weight, how many of those numbers go into whatever's given is how you calculate moles. Well, calculating mass is just a product. One's a ratio, divide by formula weight. The other one is whatever you're given, multiply by formula weight. So please work that. Once you get that, everything else falls in place. Now, there are some other things that you need to do to convert to moles, solutions. Because reactions take place in solutions for the most part. They just don't exist on paper and then exist in the real. A solution is a homogeneous mixture by definition. And it is expressed in terms of concentration, the stuff in solutions. Well, let me put the composition. It is made up of a solute and solvent. And the combination is the solution. That's what it is. Think about it, it's no big deal. The issue is, how many moles of solute do we have in the solution? It's given by one simple formula, and that is concentration, molarity. That's what's going to be given, molarity times volume expressed in liters. That's called solution data. Say a problem comes along and says I've given 25 milliliters of 0.25 molar HCl. These two go together, a volume and a concentration number. Together, you can be used to calculate moles. Because why do you want to calculate moles? So you can put it in the equation that it's dealing with, use ratio and proportion, solve for whatever they're asking for. At the end of it, you can go back. I'm sure you got to convert back. But you get this thing to moles, you got it made. Moles is molarity times volume, 0.25 molar times 0.025 liters, and whatever that comes out to be in moles. Volumetric analysis is what it's called, the type of data you get. Here's a problem, and it looks kind of nasty looking in its context. But it said, look here, what volume of 0.234 molar nitric acid will react with 49 milliliters of 0.333? See those two numbers right there? They always have to go together in a solution. You have to have a volume number, and you have to have a concentration number with a big M on it. You have to have it. And I just told you how to get that to moles. Molarity times volume in liters. Molarity times volume in liters. Now you got moles, go up there and you put it in the equation, set up your ratio, and you're through. Now you go back to moles equal molarity times volume, put in your moles you calculated, whatever the solution volume is, determine the concentration. Back and forth. Very easy to do. All right. Grams goes to moles. It's mass over formula weight. Moles to grams is moles given times formula weight. And if you've got solution data means a volume and concentration together term. Data is in volume concentration. 25 milliliters of 2 molar. That goes together. So moles here is molarity, that's a concentration term, time volume expressed in liters. Okay, now let's work a bunch of 1,000 problems. And it's just got a bunch of titles on it, and that's the one we're working with. Does everybody have a copy of this? I've got 2 or 3 more over here somewhere. So you'll need that in front of you for right now. So we're going to start with just the mole worksheet right now. Okay, what do you need? Well, the first question in here is, what's the definition of a mole? A mole is the mass of substance containing 1 Avogadro's number. And 1 mole equals 1 formula weight. So one way to put this is 1 mole equals 1 formula weight, which is equal to 1 Avogadro's number. There you go. Now, keep that in the back of your mind. All right, then he goes on, how many moles are present in 34 grams? Okay, so how many moles equal 34 grams? Okay, from grams to moles, I told you divide by formula. Wait a minute, what's the substance? Copper hydroxide. Okay, so you need to think in terms of converting that to moles. You need to divide by formula weight. That's rule 1. So, what's the formula? Yeah, this is 98 grams per mole. So moles here, copper hydroxide is equal to 34 grams divided by 98 grams per mole. Grams drop out, denominator inverts, multiplies back through, and you should get 0.35 mole copper hydroxide. Okay. Next one is, how many moles are in 2.45 times 10 to the 23rd molecules of methane? Well, this can be a dimensional analysis and revolve around this. 1 mole, 1 Avogadro's number. Now, 1 mole of molecules contains 602 times 10 to the 23rd of those molecules. Okay, so how many moles is equal to 2.45 times 10 to the 23rd molecules of methane? We need to get rid of molecules of methane, and it turns out to be 1 mole CH4, 6.02 times 10 to the 23rd molecules of methane. So molecules of methane drop out, and you're left with moles right here. So you're dividing by 602 times 10 to the 23rd. So that is 2.45 times 10 to the 23rd over 6.02 times 10 to the 23rd moles, 1 mole, methane. That, of course, drops out very, very neatly, and it's 0.41 mole. So it's a matter of using this relationship up here. Well, not the 98 in there. 1 mole equals 1 formula weight as a ratio, or 1 mole equals Avogadro's number, or formula weight equals Avogadro. Any combination can be a conversion factor. All right, this next one is how many grams equal 3.4 times 10 to the 24th molecules, NH3. Well, what did I tell you earlier? What is the definition? 1 mole equals 1 formula weight, which is equal to 1 Avogadro's number, or N is 6.02. Well, we can use this as a conversion factor against that, against the given. So how many grams equals 3.4 times 10 to the 23rd molecules ammonia? And we can use formula weight. We see molecules, that's 602 times 10 to the 23rd goes with the molecules. And the formula weight is 17 grams per mole. So we know that the formula weight equals the Avogadro's number. So now molecules will drop out, and we're left with the calculation now. And my calculations come out now. Grams. Now, what we're working with is just making some simple conversions. Why am I doing this? Because this is what you're going to have to deal with in working with equations. Yes?
The first number there, 3.4 times 10 to the 24th. You wrote it as 23rd.
Thank you. Yes, it is. I have it. And I worked them out the other day. Thank you. Yeah, keep me honest, guys, for God's sake, because I'm going. How much does 4.2 moles of calcium nitrate weigh? Well, here's where you multiply, okay, times formula weight. Moles given times formula weight, and gives you the grams. So how many grams is equal to 4.2 moles of calcium nitrate? Yeah, it's 4.2. I didn't do the formula weight. Okay. Calcium is, let's do that over here to the sidebar. 40, 28, 6 times 16, 96. 14, and 10, 40, 50, 60. 164 grams per mole. Y'all back me up on that. Well, anyway, this would be 4.2 moles times 164 grams per mole. Moles drop out. And let's see what I got. I got 689 grams. Yes.
Are you like a big heckler on significant figures? So like you're given 4.2,
Yeah.
we round to 690 grams.
Well, two answers I can give. See, the problem, yes, is based upon the data given, and you work the sig figs off the data. Yes. To save you time and worry, look at the answer choice. It'll tell you right out. Carry it out to that level. Okay. No, but you're right. You should take it into account. You're absolutely right. And we got answers in there somewhere. I thought I put them in. No, they're on another page. Anyway, mass-to-mass stoichiometry problem. All right, now you're working with mass to mass. Okay, fine. You can use any combination of that table, that big table I built a few minutes ago, as a conversion factor. And it works fine. But let's look at this. Mass to mass reaction equation problem. And just look at the pattern I used here in putting this together. Okay, you're given an equation. They don't go into all the states of existence. This is the first one. Lithium hydroxide, hydrobromic acid goes to lithium bromide, salt, and the driving force is water in there. You start with 10 grams of lithium hydroxide. Now, I used to go in and put it like this. 10 grams of lithium hydroxide. How many grams of lithium bromide will be produced? And I put whatever I'm trying to calculate in that format. Now, in this type of problem, it didn't say anything about hydrogen bromide or the water. In reactions like this, assume excess. Now, that means you got more than you need, and all of that's going to react out. That's the point. Everything's going to react. If it doesn't say anything, you assume an excess. Okay. What's the rule I gave you? Convert to moles, solve by ratio, convert to needed answer. That's what we did. That's the way you should do this. All of them. You'll see even the more complex problems. Okay, we need the formula weight of lithium hydroxide. A lot of this stuff I've documented. Photos in it. I didn't do it on that one. Oh, there it is. That's what I'm looking for right here. Okay. Lithium hydroxide is 24 atomic mass units. This one's 81. Even though you don't need it, this is 87, and this is 18. So I put those up. I'll go through and calculate formula weights and stick them above the formulas. I may need them, may not need them, but I'd rather have them than not need them and need them not have them. So that's one of the first things I'm working with equations. Just put the formula weights up there. Okay, so convert to moles. So how do we get grams to moles? Say divide by formula weight. Thank you. Okay, so 10 over 24 moles of lithium hydroxide. That's what you have. And whatever that comes out, I didn't work that one. Okay, and divided by 24. 0.42, yeah. Okay, now it wants to know about lithium bromide over here. Notice, this is what you start looking at. What are the coefficients? How do the coefficients compare? They are the same. So if you use 0.42 mole of lithium hydroxide, you're going to produce the same number of moles. Now, hypothetically, if that had been a 2 over here with the lithium bromide, and you worked out 0.42, then that would be 0.84. You would double it. But you couldn't do that. You can't just double that and say 20 grams over here. That's why moles is so useful and so simple and solves all your stoichiometry problems. Now, what do? Since we have this much produced, then we want how many grams of lithium bromide? 0.42 mole. And to moles to grams, multiply by formula weight. That's why I say it needs to be reflected. So Formula weight of that is 87 grams per mole. Moles. And 87, we were asking about lithium bromide, so I want to use that formula weight. That's 36.25. 36. What did I get? 36? Okay. Rounding it off, 36 grams. Right there. Now, in this next problem, you're given ethylene reacting in oxygen. That's a combustion problem. It always produces CO2 and water. If you have a hydrocarbon, that's hydrogen and carbon, CH something or another, NO2, it's always a combustion and always gives CO2 and water. Like that. But anyway, I went through and put the formula weights up. Now let's look at the problem. If you start with 45 grams of ethylene, okay, so we got 45 grams of ethylene. How many grams of carbon dioxide will produce? Same kind of problem. Over here. Number one, convert to moles. How do you convert grams to moles? Divide by formula weight. Divide by formula weight. Divide by formula weight. Important, huh? Okay, so over 28 grams per mole. Okay, so we have 1.64 mole. Now, how many moles will be produced over here? Well, compare the coefficients. If 1 is on the ethylene and 2 is on the CO2, that means I have to double the moles. 1 mole will give you 2 moles. So if I got 1.61 mole, then I'm going to get 2 times 1.61 mole. The coefficients tell you how to scale it up or scale it down. You may be going from high number to low number. I'll show you that in a minute. Use fraction. Okay, so mole of CO2 produced. Now I need to go from moles to grams. What do? Multiply by formula weight, right? So this would be equal to 3.22 mole times 44 grams per mole. Moles drop out. What'd you get? 141.4. That's what you said? Okay. We've got 2 sig figs in this, so it'd be 140. That's probably what would be listed in the answer collection. Okay, this is the next one. As you see, I just wrote down the equation. And above each one of the reagents, I put formula weight. Any questions? Okay, if you start with 5.5 grams of sodium fluoride, how many grams of magnesium fluoride will be produced? Okay, converting to moles, I just leave that and put 42 grams per mole. I'll tell you now. 0.131 moles sodium fluoride. Now, how does that relate? Now look at this. We got a 2 to 1. This one is a smaller number coefficient. Look at this, guys. If you're not listening, now's time. I got a 2 over here and a 1 over here. What would I multiply that number by to make it smaller so it fits this right here? Half. That's right. Now, if I'm going from magnesium fluoride, I had a moles here, going to the sodium fluoride, how much would I use? Then I would double whatever I'd have over here. So it's interesting to note that you can take the ratio. Listen, this is big time. You can take the ratio of the coefficients to adjust your mole number relative to what's logical in the equation. Relative to what's logical in the equation. What does that mean? I've got to have a smaller number over here than I started with. I start with 0.131. This number needs to be smaller than 0.131. By how much? The ratio of coefficients that will reduce it. And that is 1/2 of 0.131 moles. Whatever that is. 0.65. 0.6. And if they want to know grams, multiply times formula weight. And I get 4.6. See, it's a smaller number even when you look at the gram thing, but you can't go by that. But the mole number has to come out smaller. Gram number may come out bigger because of the elements involved have higher formula weight. Okay, so as usual, I'll go write the equation, balance it, and if the equation's not balanced, be sure to check your balance. They don't work out if you don't balance. And then put your formula weights up. You start with 20 grams of hydrochloric acid, so we're going to 20 grams here. How many grams of sulfuric acid will be produced? What we're looking for. Well, that's going to be a cut in half type thing. You can look at it. Whatever we have in moles, we have to cut it in half. So we want to get the 20 grams to moles. And that will produce half of that number, right? Because the coefficient numbers are in half. 1 goes 2 to 1, so I have to have a smaller number over here by 1/2. Now, if they're looking for grams, now we convert back to what we need. It looks like 27.2 grams calculator to 2 sig figs. 2 sig figs comes from the given data. That's where you get that. Well, actually, 1 sig fig, tell you the truth. They didn't identify the 20, so that would honestly go to a 30. You scale up. Remember how to count the? They didn't give us a decimal.